We should get started. Let's look at the magnetic field of a current. This is 32.4. So we saw a few days ago that we can represent the field of a point charge as follows. So let me remind you of that. So we have B point charge. We said this was equal to mu naught over 4 pi. And then we had Q times V cross R. This is actually R hat over R squared. So R hat is the unit normal vector in the direction of R. So this was the magnetic field of a point charge. And so we can use this to find the magnetic field of a current as a starting point. We can say that since current is the flow of charges, we can use the above formula to find the magnetic field of a current segment. So what we can do is we can say that we have, let's say we have a current carrying wire like that. It carries a current, let's say I, going through it. And so we want to find a magnetic field at some point in space. The field is going to go that way because if you wrap your right hand around the wire in the direction of the current, then the magnetic field wraps around this way. So we can say that for a segment of wire at a certain distance, R, where this is R hat, unit normal vector in the direction of R, we can find a magnetic field if we know this segment to have a length, let's say, delta S. So this segment is delta S, and this angle can be theta. So we can find a magnetic field that way. And the way I will do it is I'll start off by saying, so B for point charge is given here. It's equal to mu naught. Let me see, did I put an I? Yeah, no, there was no I. Mu naught over 4 pi. And we have Q V cross R hat over R squared. So we just take dB dt, and we can write this to be mu naught over 4 pi. And then we can say Q dq dt v cross R hat over R squared like that. And we know that since current I is equal to the charge per unit time, we can replace that in there. So we shall say dB dt is equal to mu naught I over 4 pi, and we have V cross R hat. But let's multiply divided by R squared, of course. And then we'll multiply through by dt. So we have dB equals mu naught over 4 pi. That's mu naught I over 4 pi. V dt cross R hat over R squared, where we can say that the V is equal to delta ds dt. Therefore, we can replace V dt by ds. So we can say dB is equal to mu naught I over 4 pi, and we do ds, ds not x, ds over R squared. Notice that this is a vector, so this is ds is the vector. Okay, ds cross R hat over R squared. So this will be our main formula for the Biot-Savart law for current. This is for a current segment. So this will be the basis, and of course magnetic field is a vector, so I'll put a vector notation on top of that. So this is the magnetic field of a current carrying segment. The notation used in your textbook is a little bit different, but I like this notation because it lends itself to the analysis we're going to do next. Okay. So we can use this to find the magnetic field of a current carrying wire at some point in space. Okay, so this is what we can do. So let's say we have a wire like that, and it carries a current I. Suppose we can do it anyway. It carries a current I going this way. So by right-hand rule, the field at some point in space is going to be coming out of the board. So let's say, for example, that we are along the x-axis. This is x, and this is y. So we take a certain segment of length dx, So this is the y-axis. So we are taking a segment of length dx. So it's going to be at some distance x from the axis. So we take this distance to be r. And of course, the unit normal vector is r hat pointing here. So the magnetic field at this point is coming out of the board. Let's take this to be y. Actually, let me redo this. Sorry. I want to make it easy. So delete that. Let's go this way. This is x. This is y. So I'll take this segment like that. And let's take the segment again this way. So let's put it over here on the y-axis to make it easier. So this is r. The unit normal vector is r hat. The angle is theta. This is dx. And the distance is x. So we can take this to be y. So I want to put it on the y-axis so that it will show the trigonometry very clearly. Okay. So the magnetic field at this point is this way. And we have the current going in the same direction, I. Okay. So by right-hand rule, the field comes out of the board over here. Okay. So we can use our formula dB equals mu naught I over 4 pi, and then we have ds cross r hat over r squared. So I'll translate that into the form that we have. So our dB is going to be equal to mu naught I over 4 pi, and this is going to be dx cross r hat over r squared, where r squared is equal to, what is r squared going to be equal to? If you look at it.
Y over x.
No, not y. R squared, it's not y over x. R squared. What?
X squared plus y squared?
That's right, yeah. R squared is x squared plus y squared. I'll just write it as y squared plus x squared. This is just Pythagoras' theorem. Like that. Okay. So, and then we have dx cross r hat. Dx cross r hat is just going to be equal to dx sine theta. Okay. So if you look at it this way, r hat is unit normal vector along the direction of r, and dx is in the x direction, and the angle between them is theta. So dx cross r hat is just dx sine theta. And so we can write dB equals mu naught I over 4 pi, and then we shall have dx sine theta divided by r squared, or let me replace r squared by y squared plus x squared, like that. And then if you like, let's do the integral right away. We can say that the integral of dB is b, and so this will be mu naught I divided by 4 pi, and then we shall do the integral of sine theta dx divided by y squared plus x squared. Okay, and then we're going from minus infinity to infinity. And we can replace sine theta by something else, because sine theta is going to be opposite of our hypotenuse, so it's going to be y over r. Okay, we already know r squared is y squared plus x squared, so we can use that. So r is the square root of y squared plus x squared. We take that to the power half for square roots. Then we shall say the magnetic field B is equal to mu naught I divided by 4 pi, and then we go from minus infinity to infinity. Sine theta, we're going to replace it by y over that quantity, so we shall say y here, and this is going to be equal to y squared plus x squared raised to the power 3 over 2, and then this is dx. So I've just multiplied r squared, which is y squared plus x squared, by r, which is the square root of y squared plus x squared, and that gives me the y squared plus x squared to the power 3 over 2. So for this integral, we can look at the integral table in the back of the book. So for an integral like this, the integral from minus infinity to infinity of dx, so I can take the y out, dx over y squared plus x squared raised to the power 3 over 2, I'll put a y here, and this gives me x divided by y squared, and then I'm going to have y squared plus x squared raised to the power half. Okay, so this is the integral result from what we have there. So this is from table. So the magnetic field can then be written as mu naught I over 4 pi. I'll cancel one of the y's when I put it in, so I'm going to have x divided by y, and that will be equal to y squared plus x squared raised to the power half, like that. Okay. And then I'm going to go from minus infinity to infinity for this integral. I could have done it from here too. Okay, we still have to do the minus infinity to infinity for the integral. Any questions at this point? Okay, so for infinite integrals like this, so we can say that b equals mu naught I over 4 pi. And if we take x to be infinity, then we're going to have, so let's go this way. Because at the bottom, if x is infinite, it dominates over y, so we can have x, and let me put one of the y's out here, and then we're going to have x squared raised to the power half, like that. I'll do it for positive infinity plus x over x squared raised to the power half. This is negative infinity, and so this gives me 1 plus 1, like that. Because basically, if you think of it, the way I'm doing it is that I'm saying that since x squared is larger, if I'm putting the infinity into x, then x squared is going to be larger than y squared. So I'm taking the y squared away to simplify it, and I'm just saying x over x squared raised to the power half is x over x, which is 1. So at positive infinity, I have 1, and at negative infinity, I'll also have 1, because if I put negative infinity and square it, it gets to positive. So because I'm using the infinity as a way to eliminate y, then in those two cases, I just have 1 plus 1, 1 minus 1, which is 1 plus 1, which gives us 2. Because in reality, I'm subtracting here negative, and then there will be because this is negative infinity, that puts a negative there. That's why I made it positive. So that gives me b equals mu naught I times 2 over 4 pi y, which is just equal to mu naught I divided by 2 pi y. So this is the magnetic field of an infinite line of wire. Your textbook uses d for y, so it gives you the same result. So we can also do the magnetic field of a current loop the same way. So let's try that. So we're finding the magnetic field of the current loop that I'm going to draw for you. So let's draw a current carrying loop this way. This is the y-axis. This is x. I made that too big. I don't make it that big. So let's say this is x. And we want to find the magnetic field of a current carrying loop. So this has a radius r. And let's say that it carries a current I this way. So we want to find the magnetic field at some point P. So at this point P, the field is going to point that way. So let's call this field dB. And so this field is coming from this segment here. Let's call it ds. And so this segment is at some distance r. And of course, the unit normal vector is still there. So this distance is y, and that is r. Okay, the angle here, let's put the angle here to be theta, like that. So we shall use this to find the magnetic field of a current carrying loop. So we use our formula again. We'll say this is dB, and this is equal to mu naught I over 4 pi ds. Let me just write it this way generically, and then I'll put it in the form for us, ds plus r hat over r squared again. So this is our basic formula, and so that's dB. So at this point here, the field is this way. This is dB. This angle is, I didn't come out too well. So this is our segment again. This is ds, and this ds goes that way. So I have my r this way, I have my y, and I have my r. ds is equal to r d theta. Okay, so the theta is going to be going through the loop of the circle. It's going to go around the loop. Okay, and ds cross r hat is just going to be equal to ds, because in this case the unit normal vector r hat is at 90 degrees to ds. Okay, so ds cross r hat is just going to be equal to ds, and ds is r d theta. So db at this angle is theta. So if I take db, I'll take a component dbx, and then the other component is dby. And so if this is theta, then just above that angle is 90 minus theta. So this part is also theta. And then beyond that is 90 minus theta. So that's your theta over there. So then I'll say that dbx is equal to db cosine theta. This component cancels out. So dbx is equal to 0, because the x component all the way around the loop will cancel out. And then dby is equal to db sine theta. This is the component we shall be working with. So we can say that by is equal to mu naught I over 4 pi, and then we're going to go integral of ds, which is ds cross r hat is just ds, and then we have the sine theta, so we shall say sine theta ds divided by r squared, which is just going to be equal to y squared plus uppercase r squared, like that. Okay, and then we're going to go from 0 to 2 pi next, because I'm going to replace ds by r d theta. So are you seeing everything? So the y component of the magnetic field, which is along the axis, is mu naught I over 4 pi, and then we're going to go 0 to 2 pi sine theta, which we shall replace. So let's say sine theta. Let's do that after we do this. So let's put a sine theta, and then ds is r d theta. R is the uppercase r, of course, and the d theta. This is y squared plus r squared, like that. And then we say that sine theta is equal to opposite over hypotenuse. So in this case, sine theta is r over y, uppercase r over y. So it's going to be this, no, r over lowercase r, not y, sorry. Look at the trigonometry. Sine theta is opposite, which is uppercase r over hypotenuse little r. So we can say by is equal to mu naught I over 4 pi, going from there. And before that, let's do it this way. Let me take this off. I'll put out the uppercase r. So I'll have r squared. Then I'll have y squared plus r squared raised to the power 3 over 2. And then I'll go from 0 to 2 pi d theta. So what I've done is I've taken sine theta and replacing it by uppercase r over lowercase r. Lowercase r is the square root of y squared plus r squared. And then since those are not variable, I'm not integrating over them. So I take them out of the integral sign and I'm integrating over theta. So that's how we ended up with this formula this way. So this becomes straightforward now. We are just integrating over theta. So we're going to have mu naught I times 2 pi uppercase r squared divided by 4 pi, and then we just have here y squared plus r squared raised to the power 3 over 2. So we can say mu naught I times 2 r squared, sorry, the 2 is gone, my bad, times r squared divided by 2, and then we have y squared plus r squared raised to the power 3 over 2. Okay, So this is exactly what is in your textbook. Let me see, this is in your textbook with the R squared. So your textbook uses the same R. The only difference is your book has it on the side. I just put it upright. So it's the same thing. So we can analyze this a little bit. Oh, excuse me. We can analyze this a little bit to see what happens. Say, for example, if you wanted to find a magnetic field at the center of a loop. So let's do some analysis. So if we want to find magnetic field at the center of the loop, we know the magnetic field along the axis of the loop is given by mu naught I R squared divided by 2, and then we have Y squared plus R squared raised to the power 3 over 2. So if we want to find it at the center of the loop, then we will say that at the center of the loop, Y is equal to 0. So at center of loop, we take Y to be equal to 0. Therefore, our magnetic field B at the center of the loop is going to be, let me take the Y off, sorry. Magnetic field at the center will be equal to mu naught I R squared. And what will we get if we use Y equals 0? So for Y, go ahead.
2R squared to 3.
Yes, 2R squared raised to the power 3 over 2. So what does that give us? What is R squared raised to the power 3 over 2?
R cubed, right?
R cubed, thank you. So it's going to be mu naught I R squared divided by 2R cubed. So you see you can cancel those two with 2 of those. So field at the center becomes mu naught I over 2R. So that is the field at the center. And if you have n loops, then you can multiply through by n. So we can say that for n loops of wire, then we can say the B field at the center is going to be equal to n mu naught I over 2R. Okay, so let's look at dipoles next. So we'll say we can further analyze this result in the next section. So here in this section, this is section 32.5. This is magnetic dipoles. We've already said that there is no magnetic monopole, and so all magnets, anything that has a magnetic field is basically a dipole of some kind. So we can have a north portion and a south portion to the magnetic field. So we're talking of magnetic dipoles. So a magnetic dipole is a small current carrying loop. So we'll start off saying that as a definition, a magnetic dipole is a small current carrying loop. You can see an example or an illustration of the field of a dipole. Okay, so suppose I have a current loop that is like that, with current going this way. So this current is going counterclockwise. So this is counterclockwise current. Let me write it down here. So the current is counterclockwise. So that means that if I take that loop and I put it edge to edge, then at the top part, the current is going to be going into the board. So I'll go this way. And then at the bottom, the current is going to be coming out of the board. So this means that when I'm at the top, the current is into the board. So by right-hand rule, my field is going to go like that. Okay, by right-hand rule, so the field is going to be this way. Okay, coming out. And then at the bottom, we do the right-hand rule again. And you see how I'm doing it. So at the bottom, the field is coming out of the board. So I go like this. And so my current is going this way. No, I got that wrong. Hold on a second. So at the bottom, it's coming out of the board toward you. Okay, so out of the board toward you. So yes, it's going to be going down. Out of the board. Now this is opposite. Hold on, let me correct this. This is opposite. I have it the opposite way. So I'm going like this. So at the top part, the current is into the board. So by right-hand rule, if I grab it this way, then my field line should be this way. And then at the bottom, I'm coming out, so the field lines are that way. Okay, coming out of the board, when I grab it, then my field is that way. When I grab it that way here. So I had it opposite, so now it's correct. Any questions on that? And then let's draw it on its flat face like that. So let's draw it this way. So I said the current was counterclockwise. So this is a current I, and it's going to be going this way, counterclockwise. Okay. So for counterclockwise current, then if I grab it with my right hand, then over here inside here, I'm going to be going this way. It's going to be coming out of the board, and outside it's going to be going into the board. So the field is into the board outside of the loop and coming out of the board on the inside.
Say that again?
The field is out of the board when it's in the loop and into the board when it's outside, okay, by right-hand rule. Because we've already used that convention. Remember, the convention was the field is out when it's like that, and when it's this way, the field is in. Okay, that's the convention we are using. Any questions? Okay, so that's the magnetic dipole. And so we said a current loop is a small current carrying loop is a magnetic dipole. The same thing applies to a bar magnet. So we say we already said a small current carrying loop is a magnetic dipole. Another example is the bar magnet. Okay, the bar magnet is also a magnetic dipole. So for the bar magnet, let's say, let me see. So bar magnet, let me see which one I can use. So let me try this way. So this is our bar magnet. So this is, let's put the north here and the south here. So for this bar magnet, the field lines, of course, are going to go this way. Field lines go from north to south, and field lines do not cross. So at some point, we're going to have something like this. Okay, and then they'll be coming in from this side. Okay, so that's your bar magnet. So this bar magnet will be similar to having a current carrying wire like what we had there. So this is similar to a situation where we have something like this. This time it's going to be this and that, because I want it to be such that it mimics what you have. So in this case, I'm going out of the board on top. So the field is going to be going this way. So this field is that way over here, this way here. So at the bottom, just like how we drew it at first, this is what we have. So we're going to have something like this, okay? And then it's going to be coming in at the back. So this is just like the bar magnet that we were talking about. See that? So the loop is just like the bar magnet, same sort of field pattern as you can see, okay? If I made a magnet shorter, it will look exactly the same. Yeah, so that's the whole idea. So this is a current loop, and this is a bar magnet. Questions on that? Very good. So now let's look at the formulas associated with that. Let's look at the dipole moment. So we can say that a magnetic dipole has a dipole moment, and we can has a dipole moment. The dipole moment is letter mu. Again, this time it's not mu naught, but it's mu, where dipole moment is defined as the current multiplied by the area of the loop A. Let me write it as area A of the loop. Area A of the loop. So the dipole moment mu is equal to current times area of the loop. Okay. This is a vector, so we can say dipole moment is equal to I times A, where A is the area vector for the loop. Okay, so suppose we have a loop. Let me show you this way. Suppose we have a loop this way with a current I going through the loop. Okay, the loop will have an area vector A pointing that way. This is the current I. So the dipole moment is going to be equal to current times area. Dipole moment is a vector that points upwards. Okay, so mu will point up. Dipole moment points up. I'm trying to get it's too small. Okay, so the dipole moment points up.
Oh, could you scroll back up?
Sure. Yeah. Yes. So that's fine. Okay, go down now. So we can say we can find the magnetic field of a dipole below. So let me put here magnetic field of a dipole. So we'll start off with the magnetic field we found for our current carrying loop. So we use the magnetic field of our current carrying loop. So the magnetic field of the loop was given by mu naught I over 2, and I think there was some r squared here. We had y squared plus r squared raised to the power 3 over 2. So that's what we have, and make sure mu naught I r squared over 2. So that's the magnetic field of our loop. So we can use that to find the magnetic field of a dipole. By definition, we said that the dipole is a small current carrying loop. So the whole idea is that we want to make the dipole very small. This means that we want to make the distance very long from the dipole. So we can say that we can consider the field of the dipole if we find the field at some distance y much greater than r. Okay, so if we take our point where we want to find the magnetic field to be at distance y, which is much greater than the radius of the loop, then we can say that the loop is a dipole because it's going to be small. The whole idea is that a magnetic dipole is a small current carrying loop. So if we are far away from it, then it appears as a very small loop. So we're taking y to be much larger than r. So in this regard, we can say that the magnetic field of the dipole can be written as mu naught I r squared divided by 2. And since y is much greater than r, then we shall just ignore the r at the bottom and put y squared 3 over 2. And then we'll just take that out of the under the square root and cube it. So we have mu naught, sorry, this is not cube, mu naught r squared, mu naught I r squared over 2 y cubed. So to make this into the form of a dipole, let's make some additions. So we want the current times the area of the loop. So let's multiply the top by pi and the bottom by pi. So multiplying top and bottom by pi, we get B dipole to be equal to mu naught I pi r squared over 2 pi y cubed. And since we already know that pi r squared is the area of the loop, okay, so we'll say that B dipole is equal to mu naught I times area divided by 2 pi y cubed. And we also know that a dipole moment is equal to current times area. So we'll replace that there, and we will see that the B dipole is equal to mu naught multiplied by mu divided by 2 pi y cubed. Okay, this tells us that the magnetic field of the current carrying loop is equal to mu naught. It depends on the dipole moment and the distance cubed, inversely related to the distance cubed, okay, at some far distance away from the dipole. Okay, questions on that? Now, if you want to look at it the same way as in your text, you can multiply both top and bottom by 2. Your text has an extra 2 on it, but you can just multiply the top and bottom by 2. That gives you the same result. Any questions on that? So this is the magnetic field of a dipole. So I want to save this, so because the next topic coming up is Ampere's law. Ampere's law is a way to simplify finding the magnetic fields of different symmetries of current carrying wires. So I want to save this and separate that so that we don't get the two mixed up. Okay. So take 1 minute.
What was the formula for again?
This is the magnetic field of a dipole. So let me see if I can give you an example before we end this. Let's give you something that you can try. Okay, let me give you an example exercise to try. So the first one. So we have here, I want you to find the magnetic field at some point here. This is point A. This is for a wire that is into the board here. This is a second wire coming. This one, I like to do this one out of the board. So this is a current I, which is equal to 3 amperes. This is current I equal to 6 amperes. Okay, so the two currents, one of them is coming out of the board and one of them is into the board. So these are wires, straight wires, going into the board and one coming out of the board. And then for number 2, so I'm going to give you one where the wire is this way, carrying a current I, and then the other one is a wire that way, carrying a current 2 amperes, and the magnetic field should be found at this point A. So D is equal to 3 centimeters. I'll take a look at see what you guys are doing so that I can have an idea if you know how to do it. Okay, let me start you off with a hint because I see that a lot of you haven't actually started yet. So these are wires. If you think of it, this wire is going into the board this way, and we want to find a magnetic field at a certain point. So if the current is into the board, if you grab it with the right hand, like that, then at this point here, the field is going to point downwards. Okay? And then for this point, the current is coming out, so by right hand rule, the field is pointing. So you're going to have one vector B down, one vector B up. So that's the way to start. So once you have that, then you're just going to use a formula for the magnetic field of a current carrying wire, the straight one that we found. And so your distance here is D. Actually, let me make it simpler for us. I think that let's put the point A at the center. It will be a lot simpler that way. So find it at the point A. Then this becomes your D, and that's D. That way we don't have to do any more trick. My intention was to set it up this way for you. I didn't set it up right the first time. I think this is what it should be. So find the field at this point D between the two wires. So the same principle applies. At some point, one of the fields is going to be pointing to the right and one. Oh, mu naught is permeability is 4 pi times 10 to negative 6. Is it 6 or 7? 6. Negative 7. Let me give you an idea how to do number 1. So we have the current into the board. We have the point A and the current coming out. And we are saying that this distance is just D. So magnetic field B is equal to mu naught I over 2 pi D for a straight line wire. So what you need is by right hand rule, since the top part is going into the board, by right hand rule the field is B this way. So if you take this to be 1, then it is B1. And by right hand rule, the bottom one is coming out at you. So by right hand rule, that field is this way also. Let's call it B2. So the net magnetic field B at the point A is just equal to B1 plus B2. So the magnetic field at the point A can be written as mu naught I1 over 2 pi D plus mu naught I2 over 2 pi D. So the current at the top was given as 3 amperes. So we can say I1 is equal to 3 amperes. I2 is equal to 6 amperes. So you can plug in those quantities. D is equal to 1.5 centimeters because the whole thing was 3. I gave you the whole thing as 3. So this is just D over 2. So This is D from 1, D from 2. So this you can call it D1, D2 if you like. So the D1 and D2 are equal. D1 is 1.5, D2 is also 1.5 centimeters. So that's what I wanted you to do, to use the magnetic field formula for the straight line to calculate the field at some point in space, this point here. So you have mu naught over 2 pi d, and you just do I1 plus I2, like that. So mu naught we said was equal to 4 pi times 10 to negative 7 divided by 2 pi times 0.015. Remember that this should be all in meters, and then you add 6 plus 3, this is 9 amperes, like that. So the field at that point A is the sum of those two fields. You can remove your 2 pi with one of those 2's there, and then you have 0.015 at the bottom. So you're going to do 18 amperes times 10 to negative 7 divided by 0.015. So what does that give us? Let me take the ampere out because it's going to be, the whole thing is going to be Tesla over here. So what does that give us? Say that again. 11.2?
Oh, 1.2.
Oh, 1.2, okay. So we have 1.2 times 10 to negative what? 4 Tesla. So that's the magnetic field at that point A due to the two current carrying wires. So you should be able to do something like that, find a magnetic field of two current carrying wires. The second one is done a similar way. So number 2, I gave you a wire like that and one like that, and I said find the field at this point. Okay, so this point I said was some distance D, so this is the point A. So if you have a current going this way and a current going that way, I'm going to give you a hint on how to do it. So this is the current. So let's call this I1 and I2. What currents did I give on those? Let's see. I1 is 4 and I2 is 2. So I1, 4 amperes, I2 is 2 amperes. Okay. So at this point, the rule still applies. By right-hand rule, okay, let's say this is 90 degrees. Okay, 90 degrees between them. So by right-hand rule, this one is going to point this way. This is B1. And the other one is going to point that way. This is B2. So what you have then is two magnetic fields at 90 degrees to each other. One of them points this way, B1, and the other one points that way, B2, and the angle between them is 90 degrees. So what are you going to do then? The what? Well, yes, you're going to use that. So you need to find the net magnetic field, which is this magnetic field here. This is B. So that means you're going to use what? So this is a field at the point A. So what is B at the point A? What would that be? What rule are we going to use for that?
A squared plus B squared, y squared plus x squared.
Yeah, B1 squared plus B2 squared. This is Pythagoras' theorem. So you're going to use Pythagoras to find the magnetic field at the point A, because the net magnetic field is going to be at some angle between the two of them. Do you see that? So complete this at home.
Wait, so will it be whenever you find B, just plug that in as I, or do them separate?
Yes, do the numbers first. Let's do the numbers first and then plug it in.
So find BA first and then plug it in?
So no, find B1 first and B2 first by using, so B1.
Oh, okay.
Yeah, so you're going to use B1.
Yeah.
B1 is equal to mu naught I1 over 2 pi D. The D is still the same. And B2 is equal to mu naught I2 over 2 pi D. So solve B1 first, solve B2, then put it into the formula for Pythagoras' theorem to get BA.
Okay.
Don't forget to get a direction. So The direction phi is the tangent inverse of, let's see, which one is going to be B. So this is the angle between them. Tan theta is opposite over adjacent, B2 over B1, like that. Yeah, so I'm using B2 over B1, the angle between them. So the angle is going to be phi. This angle is going to be phi. Any questions on that? Okay, let's stop here. We'll come back on Tuesday and continue with Ampere's law. That will be a